So ano, we will be moving on dun sa mga next topics natin. Okay? In which we will discuss yung stability, steady state error, root locus, tsaka frequency response for the next coming weeks. Okay. So, mamaya na lang ako gagawa ng mga announcement siguro pagkatapos nitong lahat. Pagkatapos ng lecture natin ngayon, baka gagawa tayo ng mga announcements later on. Yun. Now, so ang next topic natin is stability. Okay? And you might have noticed na uh, nailagay ko na sa inyong notebook. Okay, yung next topic ninyo which is week 8. Okay, tapos meron na rin kayong homework kung i-check niyo yung teams natin. Okay. So ang due date nun is parang October 27 yata. Okay. So ayun, pag-usapan natin later on yung mga next schedule niyo. Okay. So bali for today, ang gagawin natin is kasi nakapag-prepare na ako ng recorded lecture para dito eh. Okay. So para hindi naman masayang yung ni-record ko. We will watch them today. Okay, kung ilan yung mapapanood natin. So we will watch them today and then we will have some kind of discussion. Okay? So ayun. So eto. Let's show yung video, okay? And raise hands kung raise hands kung merong audio ah. Okay, para sigurado ako maririnig niyo yung sinasabi ng Okay, raise hands pag may audio. Okay? Naintindihan ba yan? Okay, so sige, baba muna. Pag may audio tong video. Okay, game. Okay. So far we have covered out of this design objectives ng control systems which we have enumerated at the start of this at the start of this course. We have so far covered one, okay, which is to produce the desired transient response. Okay. Now, in the next two topics, okay, in the next two sections, okay, we will cover now yung stability at saka yung steady state error. Okay, so in this case, we will first cover yung stability. Okay, and then on the next section, we will cover steady state error. Okay, so stability is the most important specification. Okay, so we should remember that without stability, okay, or without ensuring first that your system is stable, your system design is basically moot and academic. Ibig sabihin, walang silbi yung efforts natin to design the transient response and the steady state error kung unstable naman yung system niyo. Okay? So before a control systems engineer analyzes system for transient response and steady state error, he or she should be first concerned about the stability of the system. Okay, so basically, ang proseso talaga bago tayo dapat makapag-analyze is we first ensure na stable yung system natin. Okay, so far dun sa ating transient response or nung kinover natin yung transient response, we are assuming that your system is stable. Okay, and in fact, kapag naman tinest nyo lahat yung systems natin, okay, we are assured na stable naman talaga siya. Okay, pero ang totoong proseso talaga niyan is dapat we have to ensure first that your system is stable before you actually proceed analyzing the transient response and steady state error. Okay. Then as engineer moves to design the system for desired transient response and or steady state error, okay, he or she should have an idea of the extent of the changes on system parameters he or she can make to keep the system stability. So habang dire-design nyo naman, okay, so dun sa analysis part, kailangan tingnan nyo muna kung stable yung system bago nyo siya i-analyze for steady state response and for transient response and steady state error. Sa design part, habang nagde-design kayo, kailangan ini-ensure nyo na yung changes dun sa yung gagawin yung mga changes dun sa system parameters would keep the system in its stable state. Okay, otherwise, kapag ka nakuha nyo nga yung transient response na gusto nyo, pero nung pinilitan nyo naman yung yung system parameters nyo, bigla siya naging unstable, then wala rin silbi yung dinesign niyo. Okay? Now, in this section, we will define stability. Okay? Study a tool to analyze the stability of systems and design system parameters and transfer functions that will keep the system within its stable condition. Okay. Now, at the end of this lesson, you should be able to, 1, define stability and explain the necessary conditions that makes a system stable, marginally stable, and unstable. 2, make and interpret a route table. Okay. The basic one, the first row element is 0, or the entire row is 0 to determine the stability of a system. And determine the range of values allowed for a system parameter to keep the system within a stable region of its operation. So ito yung ating lesson outcomes. Okay. In the discussion of time response in the previous lesson, we have stated that the time response of a system has two components. Okay. So we have the natural response and the forced response. Okay. So that we say that the total response is the forced response plus the natural response. Okay. So we also have emphasized in the previous discussion that full control. Ibig sabihin kapag yung system ninyo is under a state na nakokontrol talaga natin siya. Okay. Is achieved if the steady state response of the system has the same form of the output. Meaning, kung ang ating input ay step, dapat ang ating output should be, kung ang input natin ay step, dapat ang output natin should be a constant, or has a constant steady state response. Okay, and so on. Okay. Pero possibly of different magnitude. Okay, so pwedeng iba yung level niya. Okay. Thus, for a full control, okay, the natural response should decay to 0. Okay, so kailangan itong ating natural response na to, okay, itong ating natural response na to should decay to 0 kapag nagkakaroon tayo or kapag ang system natin is under control. Okay. Now, from there, doon natin malalaman or doon natin madederive yung definitions ng stability, ng instability, and marginal stability. So, bali, in terms ng stability, meron tayong tatlong states. Okay. Whether your system is unstable, okay, or yung state of instability, okay, meron tayong system na stable, okay, at meron tayong system na marginally stable o yung system natin na nasa state ng marginal stability. Okay? So, an LTI system is stable. Okay? An LTI system is stable if the natural response approaches 0. Okay? As time approaches infinity. So, alam na natin yan. Dapat mag-approach ng 0 yung natural response natin as time approaches infinity para masabi natin na yung system natin ay stable. Now, if otherwise, if the natural response grows without bound, okay, as time approaches infinity, then you can say that your system is unstable. Okay? And then, finally, an LTI system that is marginally stable, okay, pag sinabi nyo ang system niyo ay marginally stable, if the natural response neither decays nor grows, but remains constant, okay, or oscillates as time approaches infinity. Kung ang natural response niyo mag-oscillate after some time, okay, at nananatili, at yung oscillation naman niya has a constant amplitude, okay, o kaya kung hindi man siya nag-oscillate, magme-maintain siya ng isang constant value, okay, then your system is said to be marginally stable. Yung natural response lang pinag-uusapan natin. Okay, so ayun, yun yung tatlong definition ng stability. But this is based on the behavior of your natural response, which madalas hindi natin talaga to madederive with direct measurements. Okay, kasi ang ma-measure lang talaga natin is total response. Okay, so we will not be able to measure this directly. Okay, hindi natin siya ma-measure ng directly kasi natural response yung pinag-uusapan. about natural response yung ginagamit as a basis of definition of stability. Okay. A better way, a more practical way to actually measure yung stability ng system ninyo is actually to look for the total response. Okay, kasi pag nag-measure tayo ng response, mas nakikita natin, okay, or mas na measure natin directly yung total response ng system ninyo. Okay. Now, obviously, kung titingnan natin yung total response, tapos alam nyo na yung input nyo is bounded. When you say an input is bounded, it means na yung value nung input ninyo has a certain finite value. Okay? So, hindi man siya mag-stay dun sa finite value na yun. At least hindi siya lumalagpas dun sa dun sa finite value na yun. So, you say that your input is bounded. Example ng mga bounded input is yung delta t. Okay? Example natin is yung delta t. Okay? Example din natin is yung step function. Okay? Example na natin step function. Okay? And then example din natin is yung sinusoidal function. Okay? Yan. Yan yung mga example natin ng mga bounded input. Yung ramp, okay, yung ramp function natin at saka yung parabolic function natin. Okay? Yan. Yung ramp function natin which is t, u of t. These two are unbounded inputs or unbounded signals. Kasi yan ay tumataas as your t approaches infinity. Okay? So itong tatlo, itong delta t, itong u of t, at saka itong sinusoidal natin, these are bounded inputs or bounded signals. Okay? So ngayon, kapag yan ang in-input ninyo, okay, if you have an input of delta t, u of t, or sin u of t, okay, and your total response, okay, and the total response does not approach infinity as time approaches infinity. Ibig sabihin, hindi umakyat sa isang unbounded value yung total response nyo. Okay. Then, we can say that the natural response is not approaching infinity and thus the system is stable. So, obviously, kapag ang ang input nyo ay bounded, at you are expecting na dapat ang output nyo is also bounded. Okay, para masabi nyo na yung system niyo ay stable. Okay? Otherwise, kung ang input nyo ay unbounded, okay, obviously, yung total response nyo should also become unbounded. Okay? Kaya lang, in that case, hindi natin masasabi ngayon kung nag-decay ba sa zero yung natural response niyo. So therefore, wala tayong conclusions dito. Okay? Basta sigurado tayo, kung bounded yung input, dapat bounded din yung output. Yun yung sinasabi natin. Okay? Pero kung unbounded yung input, hindi natin masasabi ngayon kung stable. Hindi natin masasabi ngayon kagad outright kung stable yung system nyo o hindi. Okay? So from this, we can define now stability based naman sa relationship ng input at saka ng output ninyo. Okay? So a system is stable if every bounded input yields a bounded output. Okay? We call this the BIBO, bounded input, bounded output stability requirement. Okay? So kapag bounded ang input, dapat bounded ang output. Your system is stable then. Okay? Now, a system is stable, is unstable. Okay? If any bounded input, okay, yung input nyo is bounded. Okay? Pero, it yielded an unbounded output. So, yung output niyo ay tumaas without limit. Okay? So, therefore, in that case, you can say that your system is unstable. Okay? Now, a system is marginally stable if it is stable for some inputs and unstable for others. Okay? So, actually, ang medyo mahirap i-interpret yung marginal stability kapag output yun tinitingnan. So, we will have some alternative definitions. Kaya kapag talaga nagde-define tayo o nag-aantay ng stability ng system natin, we actually look at the signals, okay? We actually look at the input and output signals, and then we actually inspect yung yung natural response kung kaya natin siyang i-isolate para malaman natin kung siya talaga ay stable o hindi. Okay? Pero again, ang pinakamagandang sign na ang system niyo ay stable is if it follows the input. Kung sinusundan ng output, okay, kung sinusundan ng output ng system niyo yung input, okay, and then you were able to achieve a full control, then you can say that your system is stable. Okay? So, kung halimbawa ang system niyo ay kung ang system niyo ay kung ang input niyo ay sinusoidal at ang output niyo naging sinusoidal din, then more or less stable yung system niyo. Yun nga lang, di natin masabi kung siya ay stable or marginally stable. So, doon lang medyo magkakaroon ng konting confusion or konting ambiguity. Okay. So, yan. Now, how can a system be concluded as stable? So, paano ba natin nako-conclude na stable yung system natin? Okay. Looking into the natural response, which is required to approach zero as time approaches infinity, it can be seen that the system poles that yield the natural response should be negative. Okay. If they are real or have negative real parts if they are complex. Okay. Obviously, yung system poles niyo that yield the natural response, dapat magde-decay siya sa zero. So therefore, kung real pole man siya, dapat negative siya. Dahil magkakaroon kayo ng yung yung pole na yon would actually generate an exponential that has a negative exponent. For example, kung meron kayong expression or meron kayong kung isa sa mga partial fraction decomposition ng system ninyo or ng response niyo would be A over S plus sabihin natin 4. Okay? Pag ito in-inverse niyo, magiging E raised to negative 40 yan. Okay? So kapag ito kasama ngayon to sa natural response niyo, obviously itong E raised to negative 40 would decay to zero. Okay? Otherwise, kung ang nakalagay sa partial fraction decomposition niyo is A over S minus 4. Okay? Ano to ng inverse Laplace transform na A over ng A E raised to 40. At yung AE raised to 40 na yan, okay, sorry, hindi niyo pala nakikita. Ayan. So, halimbawa kung meron siyang partial fraction decomposition na A over S minus 4, pag in-inverse niyan, magiging AE raised to 40 yan. Okay. And obviously, itong AE raised to 40, alam natin na ito, magkano yan? Hindi yan magdidecay, but rather, mag-i-increase yan to infinity. Okay. So therefore, that would render your system to be unstable. Okay. Ganun din kapag meron kayong complex exponential, complex poles. Okay. So halimbawa, meron kayong AS plus B over S plus sabi natin 2 square plus 4. Okay. So kapag in-inverse nyo yan, it would have something like E raised to negative 2t times cosine 2t plus A cosine 2t plus B sine 2t. Okay? So, alam natin na since ito ay negative, kahit na meron kayong sinusoidal dito, magdidecay yung dalawang sinusoids na yan because you are multiplying it with a negative exponential. Okay? Whereas, kung magiging positive siya, kung magiging positive ito, then we can say na hindi ito magdidecay to zero, but rather mag-i-increase yan to infinity as your time approaches infinity. Okay? So, yun yung requirement do sa mga poles natin. In terms ng positioning ng poles sa S-plane o sa complex S-plane, we need these poles to be in the negative side. Okay? So, yung sinasabi nga natin before na dapat nasa left half plane siya. Or dapat lahat ng system poles niyo nasa left half plane. Okay? So, stable systems have closed-loop transfer functions with poles only in the left half plane of the complex S-plane. Okay? So, dapat yung closed-loop poles ninyo, okay, are in the left half plane of the complex S-plane para siya maging stable. Okay? Those systems with at least one closed-loop pole that is on the right half plane, at least kahit isa lang. Okay? At least one. Okay? They are deemed to be unstable. Kahit isa lang at kahit konting-konti lang yung pagka-positive niya. Ibig sabihin, kahit 0.1 lang yan. Yung pole mo is at 0.1, basta positive, your system is rendered unstable. Now, systems whose closed loop poles, okay, that are on the j omega axis, meaning ando siya mismo sa boundary ng left half plane tsaka right half plane, and multiplicity of 1 are marginally stable systems. Okay? So, kung meron kayong system na halimbawa ito yung ano niyo, ay sorry. Kung meron kayong ah so ito yung ano natin, S-plane natin. Tapos meron kayong pole dito sa ating J omega axis. This is your J omega axis. Okay. Kung meron kayong pole dyan, tapos ang multiplicity nito 1, okay, you can say that your system is marginally stable. Okay. Pero kung nag-double pole siya at the same position, hindi na stable yan. Okay. So this renders your system to be unstable already. Pagka nag-double pole siya dun sa same position sa J omega axis. Okay, kasi yung mga ganyang mag-ano yan, mag-yield yan ng inverse na t sine o kaya cosine omega t. Okay, and may t na to, this t increases as your time increases. Okay, so therefore, this is an increasing function. Okay, so yung system na, halimbawa, meron kang pole dito, tapos meron kang pole sa left half plane. Okay, this is considered to be marginally stable. Okay? So as long as meron kang pole dun sa ating J omega axis. Okay? This is considered to be marginally stable. Basta wag lang sila mag-double pole. Kahit marami sila diyan, halimbawa meron pang isa dito. Okay? Meron pang dalawa diyan. Okay. Marginally stable pa rin 'yan. Basta wag lang sila magdo-double pole dun sa isang location. Okay? So ayan. So we have here an example of example of systems na na bago tayo mag-proceed, ano muna tayo? Tanong muna. Sinabi ko kanina na pwede niyong i-define i-define ang stability based sa tatlong or meron kayong pwedeng tatlong pagbasihan ng definition ng stability natin. Okay, una depende sa natural response. Okay, number two, depende sa total response. Number three, depende sa location ng poles. Okay. In terms ng natural response, how do you define stability? Or how do you say that the system is stable in terms ng natural response? Anyone? How do you say that a system is stable in terms of the natural response? Or what conditions do we need to have your system in terms of the natural response for your system to become stable? Yan. So if the natural response decays to zero, okay, masasabi natin na yung system natin is stable. Okay, okay, very good. That's for natural response. How about sa total response? What conditions do we need for your total response to be fulfilled so that yung system natin is considered stable? Okay, so given na meron kayong input, meron kayong bounded input, if the total response is hindi mag-approach ng infinity or is not or does not increase towards infinity. Okay? So that is when we say that your system is stable. Ito yung tinatawag nating BIBO stability. Okay, or yung BIBO requirement para sa ating ito yung BIBO requirement para dun sa ating sa ating stability in terms ng total response. Now, how about sa location ng ng system poles? Anong conditions ang kailangan na ma-fulfill nila so that your system is considered stable? Okay, so as long as our poles are in all in the left half plane, so you can say that your system is stable. Okay, so yan yun yung definitions ng stability natin. So sana matandaan natin yan. Okay. We have here an example of systems na na stable tsaka unstable. Okay. So yung system niyo na stable, pag nilagay niyo sa sa closed loop transfer function. Okay. Remember dapat ito gawin natin tong closed loop transfer function. Okay. So magiging 3 all over s times s plus 1 times s plus 2 plus 3. Kailangan maging closed loop yan. Tapos kukunin natin yung poles niyan, in which that would give us this one. Okay. So makikita natin yung tatlong poles natin, ito, tsaka ito. These are on the left half plane. So we are ensured na yung system ninyo ay stable. So magre-return niya ng system na underdamped, and at the same time, alam natin may full control. O meron tayong full control dun sa ating system. Okay? Kasi susundan niyo yung input ninyo na step input. Okay, so this system is stable. Otherwise, ito, okay, again, i-reduce natin ito sa kanyang closed loop form. So this becomes 7 all over s times s plus 2, sorry, s plus 1 times s plus 2 plus 7. Okay, tapos pag kinuha natin yung poles niyan, okay, we will have the following. We will have the poles here, tapos ito. Okay, meron kayong dalawang poles dun sa right half plane. Okay, meron kayong poles dun sa right half plane. So therefore, the system is unstable. So may verify niyo pag rinap nyo, makikita nyo na yung signal niyo lumalaki as your time progresses. So we will say that this system now is unstable. Okay? So, ayan. Now, determining the stability of feedback control systems is not a simple task, however. Some systems will have higher ordered faults when reduced to an equivalent closed-loop transfer function, which requires factoring and solving for the roots of the denominator of the transfer function. Pero sa atin, in the presence of computing tools such as MATLAB and Octave. Actually, hindi na masyado mahirap para sa atin 'to. Okay, kahit na meron kayong 10 poles. Okay. Kayang hanapin niya ng MATLAB tsaka ng Octave. Okay, masosolve ng MATLAB yung 10 poles na yan kapag meron kayong gamit na MATLAB tsaka Octave. Okay. Kaya lang, still, kapag ka nagde-design tayo, hindi natin magagamit yung MATLAB tsaka Octave kasi there is this system parameter na kailangan nating palitan ng value in which hindi siya directly may evaluate ng MATLAB at saka ng Octave unless i-program natin siya to do just that. Okay. So, this motivation of us na kahit na meron tayong tool to compute for this pools. Okay. Kailangan pa rin nating aralin yung tinatawag nating tool. Okay. We will study in the next lesson yung tinatawag nating route Hurwitz criterion in which that tool enables us to determine yung stability, yung state of stability ng system natin. Okay, without actually computing for the location of the poles ng ating system. Okay. Now again, ang motivation natin to study that tool is not hinged on the fact na gusto talaga nating malaman yung stability ng system natin, but rather on the design side. Okay, well, we can use that to determine yung range of values for our system parameters so that we will maintain yung stability ng system natin at malalaman natin kung kailan siya magiging unstable. Okay. So, ayan. Okay, so that's the first part. Okay, so define natin sa unang part yung stability. Okay. So basically, doon sa next 2 lessons is we will discuss yung route Hurwitz criterion at saka kung paano siya ginagawa. Okay, so proceeding now to the next lesson. Okay. Now we proceed with the determination of the condition of the stability of your system. Pero this is aside from actually obtaining yung poles or yung location ng poles ng system niyo. Kasi nga ang ano nga natin is that we can actually solve for the poles using yung ating computational tools such as MATLAB and Octave. Pero kapag ka-design, medyo may hirapan tayo na gamitin yung mga yon. Okay, dahil nga ang unknown natin is the system parameter and ang kailangan ninyo para ma-solve yung mga poles na yun is the system parameter. Okay, so this route Hurwitz criterion is very useful dun sa part ng design. That is why in spite of the presence of computational tools, okay, we need to study this tool pa rin. Okay. So there's a method by which the stability of feedback control systems can be determined without actually solving for the roots. Okay. Using the route Hurwitz criterion for stability, we can tell how many poles are in the left half plane, the right half plane, and on the j omega axis. Okay. So yun basically yung ginagawa ng route Hurwitz criterion. That is, it helps us to determine kung ilan yung poles na nasa left half plane, ilan yung poles na nasa right half plane, ilan yung nasa j omega axis. Okay. Now, the method of the route Hurwitz criterion requires two steps. Okay. So number 1, we need to generate a table called the route table. Okay. And number 2, interpret the route table to tell how many closed loop poles are in the left half plane, the right half plane, and on the j omega axis. Okay. So paano ba tayo mag-generate ng route table? Okay. So for a closed loop transfer function na binigay sa atin dito, for example, sa figure 5.2. Okay. Ito yung magiging ito yung magiging route table niya. Okay, ito yung magiging route table niya. Okay. So unang-una, kailangan naka closed loop. So meaning dapat naka single block lang siya. Okay. So remember that this should be a single block. Okay. So, ayan. Now, number 2, dapat yung denominator nyo naka-polynomial form. Ang kailangan lang naman natin dito basically is the denominator. So, kailangan yung denominator ninyo naka-polynomial form. Okay. So now, when you are preparing for or when you are writing out yung inyong route table, okay. So, gagawa muna kayo ng mga rows, okay, ng mga rows that corresponds to to the powers of S. So, magsisimula kayo dun sa pinakamataas na power ng S, which is S to the fourth in this case. Okay? Tapos, S cube hanggang S raised to 0. So, yun yung constant. Okay? Now, yung coefficients ngayon, okay, the coefficients ngayon, ilalagay nyo dito. So, ang arrangement is, ito yung coefficient para sa S to the fourth, ito yung coefficient para sa S cube, ito yung coefficient para sa S squared, ito yung coefficient para sa S, tapos ito yung coefficient para sa constant. So, kung meron pa nang iwan na isang space, consider that to be 0. Maliwanag yung placement na yon sa initial layout ng route table. Okay, so ipi-fill out muna natin yung first two rows. Okay? So, first column, first row, tapos first row, second row, tapos susunod is first row, second row, first row, second row. So, ipi-fill out nyo muna yung first two rows ng mga coefficients. Ganun yung pagsisimula ng route table. Okay? So, hopefully maliwanag yun. Okay, and in fact, yung iba pang entries naman yun dito is also 0. Okay? So, ayan. So, that's initially, yan yung layout ng ating route table. Okay? Then, how do we proceed with the computation or how do we complete this route table? Okay? So, para ma-complete natin yung route table na yan, ganito ang computation. Okay? So, we start with yung third row kasi nandun tayo sa kanina. So, na-complete natin yung first two rows. Okay. So, dun tayo sa third row. So, determinant ito, or negative, negative determinant ito ng A4, A1. Okay. So, ito. Okay. Ito. Tapos ito. Okay. Then, ito, tsaka ito. So, negative determinant siya nun. Okay. Divided by A3. Okay. So, ayan. So, that will be your B1. Okay. So, meron magiging B1 yun. Okay. Ito naman, yung next column naman natin is ito. Okay. Ito. For the first column of your determinant. Tapos ito. For the second column. Divided by A3. Okay. So, notice na dito. Okay. Yung ating second column. Okay. Is basically yung preceding column nung ninyo. Yung next column nung ini-evaluate niyo. Pero yung first column niya, constant na ito. Okay, so that is why, ito, para ma-evaluate ito, so again, constant yung first column. Okay, pero ito, should have been from here. Kasi wala naman ang entry dito sa 0 and 0 na siya. Also, the denominator is constant. Okay, so ang iniiba natin is yung second column. Okay, yung iniiba natin sa second column. So, halimbawa, dito rin. Okay, dito rin. So, this is A3, B1. Okay, so A3 at saka B1. Okay, so ito yung first column ninyo. Tapos yung ito, A1 tsaka B2. A1 tsaka B2, ito siya. Okay, which is yung next column ninyo. Okay, tapos ang divisor ninyo dito is basically B1. And don't forget, this is the negative determinant. Okay, so ito ganun din. Constant, yun pa rin yung first column ninyo. Then ito, okay, is 0, 0 kasi 0 na to, tsaka 0 na to. Okay. So again, constant itong B1 as your denominator. And so on. Hanggang sa matapos nyo yung row ng S raised to 0 or yung row ng constant. So, dyan matatapos ngayon yung pag-evaluate nyo ng route table. Okay? Yung pagkompleto ng route table, nakuha ninyo? Okay. So, mabuti kung nakuha ninyo. Pero kapag di nyo pa nakuha, okay lang kasi pag nag-example naman tayo, mas makukuha nyo siya. Okay? Hindi tayo gumagamit ng Kramer's tool. Ang ginagamit natin is determinant. Kinukuha lang natin yung determinant nung mga yun. Okay? Ang Kramer's tool, ginagamit yan para mag-solve ng linear equations. Okay? So, ayan. So again, kung hindi siya nakuha dun sa ano, dun sa part na 'yon, okay, dun sa part na 'yon. Panoorin niyo mabuti yung nandun sa example. Okay, dun sa example kasi mas malinaw kung paano kumuha ng ano, ng or paano magkumpleto ng route table. Okay? So ayan. So, let's have an example para dito sa ating ano, sa ating system na 'to. Okay. So, first, ano natin siya, i-express natin siya as a express natin siya as a ano, as a closed loop transfer function, which in this case this should be T of S equals 1000 over S plus 2 times S plus 3 times S plus 5 plus 1000. Yan. Or kung i-expand natin ito, this is basically, so multiply natin siya dito, no? So S plus 2, S plus 3, this is S square plus 5S plus 6. Okay, then multiply natin with S plus 5. So this is S cube plus 5 plus 5, so that's 10S square. Okay, 10S square plus 6 plus 25 plus 31S. Okay. Plus 30 plus 1,000, so 1,030. So ito yung magiging denominator nito, no? Okay, so S cube plus 10S square plus 31S plus 1,030. Okay, so yan yung ilalagay natin dito sa ating route table. So pag ginawa natin yung route table na to, okay, para dito, we will have these rows. Okay, so S cube, S square, S at saka S raised to 0. Okay, so ito ngayon yung coefficients natin, 1, tapos 10, tapos 31, at saka 1,030. Okay, and then of course dito 0 na yan. So pwedeng hindi nyo na ilagay ito eh. Okay. Now, it is a rule, ang allowed sa route table ninyo na mag-divide kayo ng positive number in any of the rows. Okay. Ang purpose nun para mas lumiit yung number ninyo. Okay. So, pwede kayong mag-multiply or mag-divide ng positive number sa isang row. Okay, so in this case, yung ginawa dito is, so 10 ito, tsaka 1,030, nag-divide siya ng 10. Okay, so 10 divided by 10 becomes 1. Tapos, 1,030 divided by 10 becomes 103. So, allowed yun. Okay, basta ma-divide nyo siya yung entire row ninyo. Okay, so now we compute now ito. Okay, as 1 times 103. Okay. So ito that becomes negative 1 times 103. 103 minus 1 times 31 divided by 1. Ito 'yun. Okay. So that's 103 minus 31. Okay. That's negative nun. That's divided by 1. That should be negative 72. Okay. O kaya, actually, yung ginagawa ko dito is para hindi ko na masyadong minamind yung hindi ko na masyadong inintindi itong negative na to. Ang ginagawa ko dito is baliktad. Ginagawa ko tong 1 times 31 minus 103 times 1 times 1. So, ginagawa ko na siyang 31. Ginagawa ko na siyang 1 times 31 minus 103 times 1 divided by 1. Kumbaga, binabaliktad ko na itong dalawang to para hindi ko na i-account itong negative na to. Okay, so yun yung isang technique na ginagawa ko pagka nagko-compute tayo ng route table. Okay, so doon na nga lalabas yung negative 72. Okay, so dito naman, this is 1 times 0, so that's 0, tapos minus 0 times 1. Okay, so 1 times 0, parang mali ito. 1 times 0. Kasi ito, dapat, actually dapat 1 to eh. Ayan, dapat 1 to. Hindi 0. Ayan. So 1 times 0 dapat. 1 times 0 minus 0 times 1. Divided by 1. So 0. Ito rin. 1 times 0. Okay, so 0 na to. So negative 72 ito. So ito, yung negative 72. Okay. Then, next is, dito tayo. So, I'll have negative 72 times 103. Okay. Minus, minus 1 times 0, 1 times 0 divided by negative 72. Okay, so that should become 103. Okay, so magiging 103 na siya. Ito. And then of course, 0 na to, 0 na to. Okay, so ang advice ko sa inyo is kapag ka 0 naman, huwag nyo nang ilagay yung 0 kasi mapupuno lang ng 0 yung, yung route table niyo. So ang ilagay nyo lang is yung mga non-zero. Okay, so kapag ka sinulat natin yung route table natin, pag sinulat natin yung route table natin, so this is S cube. So, ayan, kapag ka tinanggalan natin yung pag tinanggalan natin yung mga computations natin, yan yung mabubuo yung route table. Okay. So, another technique na pwede kong ituro sa inyo kapag ka nagko-compute kayo is ganito. Usually, or lagi naman, kapag ka ito ay 0, halimbawa 0 na to, no? 0 na to. Lalabas, itong nasa ilalim nitong negative 72 na to is, ito na siya. Kumbaga, pwede nyo ito, dali na kagad dito. Basta 0 yung nasa ilalim. So, meron kayo dito, dito, tsaka dito, tapos 0 to. Okay. Automatic na yung magiging sagot dito is ito. Okay, pwede nyo namang prove yan mathematically, pero yun na yung isa sa mga technique na natutunan din natin habang ginagamit natin yung route table ng paulit-ulit. Okay, so ayan. So, ito na yung kompletong route table natin. Okay. So, what is next after we are done with the route table? Okay. So, this is now the time that we will have to interpret yung basic route table. Okay. So, the basic route table applies to systems with poles in the left half plane and the right half plane. Okay. When you say basic route table, ito yung walang mga zero sa first column. Okay. So, mamaya i-discuss natin yung mga cases na meron kayong zero sa first column at saka yung entire row ninyo magiging zero. Okay. Those are the two special cases of the route table. Pero in this case, we are dealing with a route table na basic pa lang. Okay. So, simply stated, the route Hurwitz criterion declares, ito yung route Hurwitz criterion talaga. The route Hurwitz criterion declares that the number of roots of the polynomial, that are in the right half plane, is equal to the number of sign changes in the first column. Okay, again, the number of roots of the polynomial that are in the right half plane, is equal to the number of sign changes in the right or in the first column. So, ang gagawin natin is pipilangin natin kung ilang beses nagpalit ng sign sa first column yung inyong route table. At yung number of sign changes na yon would actually equal to the number of roots or number of poles na nasa right half plane nung complex S-plane niyo. Okay, so balikan natin to. Bibilangin natin dito ngayon kung ilang sign changes meron siya. So when you say sign changes, yung positive naging negative o yung negative naging positive. So halimbawa ito, from here to here, positive to positive, so hindi to bilang. Then from here to here, positive to negative, so that's one sign change. Okay? And then from negative to positive, that's another sign change. Okay, so yung number of sign changes natin, the number of sign changes that we have is 2. Okay, that also means that the number of poles in the right half plane for this system is actually 2. Okay, and since kung titignan natin, meron tong tatlong closed loop poles kasi S cube yung pinakamataas eh. Okay, so if we have 3 closed loop poles, yung dalawa doon nasa right half plane. Okay, yung isa ngayon automatic nasa yun? Nasa left half plane yun. Number of poles sa left half plane equals 1. Kasi nga dapat tatlo yung closed loop poles natin. Okay? Okay. So, bago ako mag-proceed, maliwanag ba 'yon? Yung interpretation ng route table. Okay. So, good. Wala bang questions so far? Miss Jaime, may question ba? Wala naman. Okay. So, walang questions ha. Tuloy natin ha. We verify with MATLAB kung tama yung results na nakuha natin. So again, tandaan natin na based sa route Hurwitz criterion, nakakuha tayo ng dalawang poles sa um, right half plane, tapos isang pole sa left half plane. Okay, so ginawa natin, kinuha muna natin yung ating forward transfer function. Okay. So ito yung magiging forward transfer function natin. 1,000 over s plus 2 times s plus 3 times s plus 5. Okay. And then using feedback, okay. Kinuha natin yung closed loop transfer function which returns na ito. Okay. And then we computed for the pole. Okay, for the poles of the closed loop transfer function. In which case it would return negative 13.4136 at saka 1.706 plus or minus 8.5950 J. So nakita natin na yung real part ng ating dalawang complex pole ay positive. So therefore, that puts them at the right half plane of the poles. So mabe-verify nyo yun kapag apply natin yan using PC map. So ito siya. Okay, so ito yung dalawang poles niyo sa right half plane, ito yung sa left half plane. Verifying yung results na nakuha natin sa ating route Hurwitz criterion. Okay? So, ayan. So, ang conclusion natin ngayon dun sa ating is that your system is unstable. Okay. So, mabe-verify niyo yun kapag kinuha natin yung step response ng ating T. So, step T. Okay. Makikita natin na unstable siya kasi as your time progresses, makikita natin na lalaki siya. Okay. Palaki ng palaki yung ating response. Okay. In fact, punta yan na ito sa 10 raised to 25. Okay. So, makikita natin yung scale nung natin is 10 raised to 25. 30 seconds pa lang yan. Okay. So, sabi natin mga 40 seconds plus. Okay. So, unstable talaga ito. Okay. So, ayun. Now, let us make a route table for the following polynomial and tell how many roots are in the right half plane and the left half plane. So, ito yung ito yung polynomial natin. Okay. So, we start off by the first two rows. So, since s raised to 7 ito, okay. Since this is s raised to 7, simula tayo ng s raised to 7 dun sa ating table. Okay. And then, we fill up the first two rows. So, 3, 9, 6, 4, 7, 8, and 2, 6. Okay. Now, what would happen is that pag kinompute natin ito, that should be 9 times 6 minus 3 times 4 divided by 9. Okay? So, we have 14 over 3 or 4.6667 nga. Okay. So, actually, kapag may decimal, dalawang choices natin. Okay, dalawang choices natin. Either i-turn natin ito sa isang whole number by multiplying this with a certain uh, number that would make them whole number. Halimbawa ito, pag multiply natin ito ng 3, magiging 14 to. So okay yun. Kasi positive number naman yung pinag-multiply natin. Again, you can multiply or divide any row by a positive number. Okay, or a positive integer. Okay. So pero ano, in this case, pwedeng iwanan na lang natin siya as is. Okay. Basta ang importante, siguraduhin niyo lang na hindi mababago yung sign nung nasa unahan. Okay, kasi halimbawa lalo na kapag masyadong maliit ito. Okay, pag masyadong maliit 'yan, it is possible that yung rounding off error niyo can actually change signs. Okay, so dapat careful kayo dun sa rounding off nung mga ganito, nung ganitong part dahil yun na nga, baka mabago niyo yung sign accidentally. Okay, kailangan hindi mabago yung I mean when I say mabago yung sign yung sa computation kailangan eksakto yung pagko-compute niyo so that the sign wouldn't be affected. Okay, so ayun. Kaya okay lang naman na naka-decimal siya. Okay, okay lang na naka-decimal siya. Pero careful lang kayo sa pag-round off. Okay. So recommendation ko is 4 decimal places or 4 significant figures para hindi para medyo safe. Okay. So ito na nga yung 4.667. Okay. So next, ito can be obtained by how do we compute yung next column na yan? Pabigay nga ng formula para ma-compute natin yung next column na yan. Ito. Yung nag-return ng 4.3333. Yung pag-groupings nyo ng baka mali yung pagkakaintindi natin ng check nyo yung groupings ng terms ninyo. Okay, check natin Again, yung formula ninyo, ang sinasabi is determinant. So kapag determinant kasi, dapat 3 times 8 minus 9 times 7. Pero tatandaan nyo, nasa formula nyo rin na negative siya. Okay? So dapat may negative. Yung sagot ni Mr. Verha at saka yung sagot ni Mr. Pangatungan, dapat may negative yan sa unahan. Okay? Dapat may negative yan sa unahan bago nyo wag nyo kakalimutan yung negative na yon. Okay? Dito, ang reason ko kung bakit ko siya binaliktad, yung pagkaka-evaluate ko ng determinant is binaliktad ko kasi nga gusto ko nang i-take negative na yon. Again, kapag ni-negative ko to, pag pinasok ko yung negative, for example, pag tinignan niyo yung sagot ni Mr. Berha or ni Mr. Pangatungan kanina, pag ni-negative ko yan, magbabaliktad tong 9 times 7 tsaka yung 3 times 8. So magiging 9 times 7 minus 3 times 8 yan. Ganun yung mangyayari. Okay, yung kay Mr. Havil, grouping lang yung problema nito. Pero kasi pag ito yung pinasok niyo sa calculator, baka iba yung lumabas Okay? So, yun titingnan niyo mabuti titingnan niyo mabuti kung bakit ko siya binabaliktad. Okay? Kung bakit ko binabaliktad yung pag-evaluate ng determinant. Okay? Ang tamang formula, okay, is negative ng 3 times 8 minus 9 times 7 divided by 9. Okay? Pero pag in-evaluate niyo siya at medyo slightly binago niyo siya, yun nga, magiging, ito siya. This is 9 times 7 minus 3 times 8 divided by 9. Okay? So that should give you 63 minus 24 divided by 9. So, that's 4.3. Okay? And then, obviously, ito, okay, this one is 0 kasi yung, okay, hindi pala. Hindi pala obviously 0 to kasi, no, that becomes 9 times 2, okay, minus 3 times 6, okay, divided by 9. And this is 18 minus 18. So, 0 yun. Kaya magiging 0 to. Okay. And then, ito yung sinasabi kong 0 na. Okay. Ito yung sinasabi kong 0 na kasi yung kasunod niya dito, 0 na rin. So, that's 9 times 0 minus 3 times 0. Okay. Again, mapapansin nyo na yung instead na ang determinant ko is 3 times 4 minus 9 times 6. Okay. Ginagawa ko siya 9 times 6 minus 3 times 4 kasi nga, tinitake into account ko yung negative determinant. Okay? So, kaya nakabaliktad kaya kung nagko-compute kayo ng determinant, medyo baliktad yung ginagamit natin dito. Dahil nga, ina-account natin na negative determinant siya. Okay? So, ayan. Now, ito yung sinasabi kong, sige, mamaya na pala. Ito muna, 9 times ito, okay. So, ito tsaka to, tapos ito tsaka to, para ma-compute natin to. Okay, so this is, this should be 4.6667 times 4 minus 9 times 4.3333 divided by 4.6667. Okay. So, pag in-compute natin yan, that becomes 4.6667 times 4 minus 9 times 4.3333 divided by 4.6667. That should give you negative 4.357071. Okay. So, ayan. Okay. Then, next ito. Ito yung sinasabi ko sa inyo na kapag ka 0 naman ito, pwedeng ito, ibaba nyo na lang dito. So, since 0 naman to, ito, pwede nyo ibaba yan. Kasi ganito mangyayari dyan. That becomes, ang computation yan is 4.6667 times 8 minus 9 times 0 divided by 4.6667. So, magsisira naman to, tapos magka-cancel ito. Kaya may iwan doon 8. Okay, kaya ito rin yung magiging 8 dito. Okay, so kapag ka 0 na yung nasa ilalim nun, pwede nyo ibaba yan. Katulad nito, ganun din to eh. 9 ito, tapos ito, tsaka to. So, since ito, 0 itong nasa ilalim, ito ngayon, pwede nyo ibaba dito. Okay? So, yan. Now, you just need to complete this table to verify na ito nga yung magiging values or close to that yung magiging values ninyo. Okay. And then from there, let's count the number of sign changes. Okay. So, yung number of sign changes natin is ito, isa. From positive to negative. So, isa, then dalawa, then tatlo, then apat. So, you have 4. Number of sign changes, you have 4. Okay. So, therefore, number of right half plane poles, number of poles at the right half plane, that would be 4. And the number of left half plane poles or roots dito kasi polynomial na pinag-uusapan natin. So that would be 3. Kasi 3 dahil 7 ito eh. So we are expecting na meron tayong 7 roots. Okay, so yung 4 doon nasa kanan, yung 3 na nasa kaliwa. Okay, pwede nyo ring i-verify yung yung location yan. Okay, using roots function sa roots function sa MATLAB or sa Octave. So input nyo lang dito yung array ng coefficients. Okay, so ayun, may verify nyo yung roots. Then may verify nyo na 4 doon ay may positive or located sa right half plane, yung 3 doon located sa left half plane. Okay. So that's for your basic route table. Okay. So sa next topic, pag-aaralan natin yung mga special cases ng route table niyo. Ayun, may question ba doon sa basic route table? Yes, Mr. Fortunato, may question ba? Okay, so kung wala, let's proceed with the special cases of the route Hurwitz criterion or the route table. Okay. Okay. So now we proceed with the special cases of your route Hurwitz criterion. Okay, in which dalawang special cases yung pag-uusapan natin. Okay. Number one uh, the route table can sometimes will have a zero only in the first column of a row. Okay, so sa isang row, yung first column nun magsi-zero. Okay. So naging special case yun kasi kung maalala nyo, lahat ng yung elements natin sa first row, ginagamit natin as a divisor para makuha nyo yung next row. Okay. So kapag ka nag-divide by zero kayo, syempre magkakaroon ng problema doon. Okay. Or number two, the route table sometimes will have an entire row of zeros that consists of will have an entire row that will consist of zeros. Okay. So, yun yung dalawang special case na pag-uusapan natin. Okay. So, for the first one, zero only in the first column. Okay. If the first element of a row is zero, okay, division by zero would be required to form the next row. Okay. To avoid this phenomenon, an epsilon or this symbol, okay, is assigned to replace the zero in the first column. Okay, then the value of epsilon is then allowed to approach zero from either the positive or negative side, after which the sign of the entire of the entries in the first column can be determined. Okay. So halimbawa, meron tayong case dito. Okay. So let's determine the stability of the closed loop transfer function of this one. Okay. So kapag tiningnan natin yung ating route table for this one. Okay. So we will have okay, so we will have 1, 2, 3, 6, 5, 3. Okay, as yung coefficients ng natin, ng ating closed loop transfer function. Okay. Now, so evaluating ito, okay, we will have 2 times 6 minus 1 times 3. Sorry, 2 times, sorry, mali pala. 2 times 3, okay, minus 1 times 6 divided by 2. So this is 6 minus 6 over 2, that's 0. Okay. Then bago kayo conclude okay ng either itong first case o second case, tingnan niyo muna yung susunod na element. Okay, so yung susunod na element diyan is 2 times 5 plus minus pala 1 times 3 divided by 2. So that should give you 10 minus 3, that's 7 over 2. So ito yung 7 over 2. Okay, and then obviously itong pangatlo to is 0 na. Okay. So in which case, meron kayong 0 on the first column. Okay. So kahit na 0 ito, okay, ito hindi to 0, non-zero ito. So this falls under the 0 only in the first column case. Okay. So ito yung first special case na gusto nating itake. Now, ang problema nga nito is that kapag 0 ito, yung next row natin is evaluated by dividing 0 dun sa ating elements sa next column. So that would not be possible. So ang gagawin natin is that we replace that 0 with a number called epsilon. Okay, yung epsilon na yan is made to be a very very small number. Okay, a very very small number. Now either siya ay positive or siya ay negative. Okay. So tingnan mo natin ano mangyayari kapag naging epsilon yan. So we will evaluate now ito as 6 epsilon, okay, minus 2 times 7 halves, so that is 7, divided by epsilon, okay, and then ito, okay, again, this would be 3, again, this is 2 epsilon, tapos 3, tapos 0, so ito, pwede natin i-carry over dito, okay, so next, we will have ito yung medyo complicated dito ng konti, no? So, we will have 6 epsilon minus 7 divided by epsilon, okay, times 7 over 2, okay, minus 3 epsilon, okay, divided by 6 epsilon minus 7 divided by epsilon. So, pag in-evaluate natin siya by some algebraic manipulation, makukuha natin ito. Okay, so paki-verify na lang kung tama. Okay. And then, of course, this is 0 na dahil 0 itong dalawang to. Okay, and then 0 din to dahil 0 na yung kasunod niya. And then, finally, para dito, we will have this to be carried over here. Kasi nga, ito, at saka ito. Ito, tsaka to, 0. So, ito, pwede rin ibaba dito. Okay. So, now, we are now able to evaluate yung first column. Okay. We are now able to evaluate itong first column natin. Okay. So, what would happen then is that itong epsilon, papalitan natin siya ng very small positive or negative number. So, kukunin natin yung first column ngayon dito. Okay, and then tingnan natin ngayon, what if this is a very small number na positive? So, positive siya. I-assume natin na yung epsilon natin is positive. Now, if this is a very small number, itong 6 times a very small number would be actually very small. Okay? So, you can imagine na itong epsilon nyo is actually, halimbawa, positive 0.0001. Okay? So, pwede nyo gamitin yun to evaluate here. Okay? So, halimbawa, 6 times positive 0.0001 minus 7 over ito. Okay? It would turn out na pwede natin i-check yan using your calculator. So, yan. So, ginamit natin yung calc function. Okay. So, tinamit natin 6x minus 7 over x. Calc 0.00001. Okay. Turns out na negative siya. Okay. So, lalabas ngayon, negative itong negative siya. Okay. So, pwede nyo gawin yung sa mga susunod. Okay. By assigning a certain small number dun sa ating epsilon. Okay. So, then, malalaman natin na yun na nga, positive, negative to. Tapos ito magiging positive, ito positive. Okay. So, we will find out na meron 2 sign changes. So, we will have a sign change here, from here to here. Okay, and then from here to here. So, you have 2 sign changes. Okay. Okay. So, kapag ginawa nyo siyang negative, ganoon din. Makakuha rin kayong dalawang sign changes. So, kung negative ito, sabihin natin gawin nyo yung negative 0.00001. Okay. So, dito pa lang, from here to here, magiging negative na siya kasi nga negative yung inassign yung number. Pero pag kinumpute nyo yung next, magiging negative, magiging positive na siya. And then ito, magiging positive na rin and so on. So, magiging dalawang sign changes na yan. Okay. So, either yung epsilon nyo is positive or negative, you will have 2 sign changes and therefore there will be 2 sign changes. So the number of sign changes is 2. Therefore, the number of poles at the RHP is 2 and the number of poles at the LHP is 3. Okay? 3 kasi dapat yung number of poles sa RHP at sa LHP all in all dapat maging 5. Dahil S raised to 5 yung pinakamataas nating degree. Okay, so you will have that one. Now, so medyo napansin niyo na medyo hindi ganoon kadaling na maglagay ng epsilon kasi nga nagiging algebraic siya. Okay. So para numerical pa rin yung solution niyo. Actually, in the evaluation of the route table or kapag in-evaluate itong route table, pwedeng ito directly palitan niyo na to ng number na maliit. Palitan niyo na kagad siya ng 0.0001. Okay? Instead na gawin nyo pa siyang epsilon. Kaya lang, dalawang beses natin gagawin ito. Isang positive, isang negative. Okay? So, ayun. Halimbawa, ito na nga yung natin, yung ating route table. Sinimulan ko na siya. Okay, so 1, 2, 3, 6, 5, 3. So again, pagka kinumpute natin ito, okay, itong part na to, this becomes 0. Okay, pero in this case, instead na 0 yung epsilon yung ipapalit ko sa kanya. Ipapalit ko sa kanya is 0.0001 instead. A positive small number. Okay, so that pag kinumpute natin ito ngayon, that becomes 0. 0.0001 times 6, okay, minus 2 times 3.5 divided by 0.0001. So that should become negative 63,994. So yun yung lagay natin dito. So let us make this as negative 63,994. Okay, and then ito magiging 3 na to kasi ito i-bring down na lang natin to dito. Okay, again 0 kasi ito. Okay, now in this case this becomes that should become negative 63,994 times 3.5, okay, minus 3 times 0.0001 divided by 63 or negative 63,994. That should give us 3.5. Okay, positive 3.5. So you would have 3.5 here. Okay, and then ito ay 0. Okay, this is 0. Dahil 0 itong dalawa, so 0 ito. And then this becomes 3. Okay, so from there, makukuha natin ngayon na meron tayong isa, okay, and then dalawang sign changes. So you know, the number of sign changes na meron tayo, or the number of sign changes na meron tayo equals 2. Okay, so therefore, the number of right half plane poles, okay, is 2. And then the number of left half plane poles is 3. Kasi 5 itong ating highest degree. Okay. Now, ang gagawin nyo ngayon is uulitin natin yan, but this time, this is negative. Okay? This is negative now. Okay? So, tingnan natin. Okay. So, in this case, again, papalitan natin to ng yung 0 dito. Okay, papalitan natin ng negative 0.001. Okay. And then, still, this is 3.5. So, ngayon, pag kinompute natin ito, that should become negative 0.0001 times 6 minus 2 times 3.5 divided by negative 0.0001. That should give us 70,006. So, dapat ito maging 70,006 ito. Okay, so this is 70,006. Okay, and this one is still 3. Okay, kasi mabibring down natin siya dito. Okay, this one, okay, becomes 6 times 3.5 minus 3 times negative 0.0001 divided by 70,006. That should give us 3.5 din. Okay, so this is 3.5. This is 0, and then this is 3. Okay. So again, counting the number of sign changes, you would have 1, okay, and then 2. So you still have the number of sign changes, okay, to be 2. Therefore, the number of right half plane poles is equal to 2, and the number of left half plane poles equals 3. So ganun pa rin. Okay, so whether we change it with a positive or negative number, yun yung yun yung makukuha natin. Okay, and still, instead of changing this to epsilon, directly palitan nyo na siya kagad ng small number. Okay, so it won't una, mas madali ito dahil numerical pa rin yung solution niyo. Okay, that's number 1. And number 2, it doesn't change yung yung ating results. Okay, so yun nga lang, kapag ganito, pwede palitan niyo siya ng positive tsaka ng negative number para sure kayo na dalawa lang yung na pareho yung results niya. Okay, now paano pagka hindi pareho? Actually, napakadalang nung case na hindi yan magpapareho kasi syempre fixed naman yung location ng poles niyo. Okay, hindi naman nagbabago yung location ng poles niyo. May question? Sir, dun po ba siya nag-zero na part sa may S cube? Okay, pwede din pong positive. Ang ginawa natin is pinalitan natin siya ng small positive at saka ng small negative number. Okay, ito yung part na negative na yung pinalit natin. Pero yung nauna dito, pinalitan natin siya positive number ang ipinalit natin. So pinakita natin yung yung results niya na pareho na lalabas. Okay? So I was explaining dito sa sa part na to is that there are very few cases na magpapalit siya ng results kapag pagka positive yung pinalit nyo, negative yung pinalit nyo. Depende do sa depende kung napakalapit nung isang pole. Okay, although naturally dapat hindi naman talaga siya nagpapalit ng position kasi hindi naman dependent sa kung ano man yung ipapalit nyo dito, yung position ng pole niyo. Pero kung tutusin, dapat hindi siya magpalit ng position. Dapat pareho pa rin yung results niya. Pero meron pa rin kasi meron pa rin dahil nga nagkakaroon kayo ng error pagdating sa sa rounding off. Okay, so may possibility na baka yung rounding off error ninyo dahil nga napakaliit ng number na nilagay ninyo, baka mag-cause ng magpalit ng results yung route table route table interpretation niyo. Okay, yun yung pinapaliwanag ko dito. Pero doon sa tanong ni Mr. Havil, naipakita na natin sa unang part nito na positive yung ipinalit ko. Okay? So, ayun. Tapos ito yung part na negative naman yung pinalit natin. So, dalawang beses natin ginawa ito. Isang positive, isang negative. Okay. Nasagot ko ba yung tanong? Okay, sige. Depende dyan sa epsilon. Okay. Kumbaga, pag binigay sa inyo yung polynomial, fix na yung location ng position. So, supposedly dapat hindi mabago yan. Okay. So, I don't know kung merong case na yan ay nababago. Okay. Although there is still this very small possibility na baka mabago siya. Especially kung medyo alanganin yung location ng isang pole. Lalo na kung nasa gitna talaga siya. Okay. Or yung malapit talaga siya sa gitna. So, baka pwede. Okay. Pero as of now, sa tagal nating tinuturo itong hindi pa naman ako nakaka-encounter ng na nagpalit ito ng results. Okay, or yung mga ganitong case nagpapalit ng results. Okay. So that's one way we can solve this we can solve this case na meron tayong zero only in the first column. Okay. So ayan. May alternative diyan. Okay. May alternative way of actually solving that case. Okay. That is we obtain a polynomial that has roots reciprocal of the original polynomial. Okay, which may not arrive at a route table with a zero only in the first column. Okay, so ang gagawin natin is ganito. Kung meron tayong polynomial, okay, at meron siyang roots, okay. Pag kinuha natin yung reciprocal ng roots natin, hindi naman napapalitan kung nasaan nakalocate yung poles natin. For example, ganito. Yan. For example, real poles muna tayo, pero this also applies to imaginary poles o to complex poles, okay. Pero sa real poles, kapag meron kayong say poles sa -2 at -3. Pag kinuha niyo yung reciprocal nitong -2, that becomes -1/2. Okay, kasi pag kinuha niyo yung reciprocal nitong -3, that becomes -1/3. Tama ba? Okay. Now, mapapansin niyo na negative pa rin sila. So ibig sabihin hindi siya nagpalit ng location. Ay nagpalit siya ng location pero hindi siya nag-crossover sa right half plane. Kumbaga nandito pa yung -1/2 tsaka -1/3 nandito pa rin sa right half plane. Okay, so ito yung -1/2 ninyo. Ito yung -1/3 ninyo. Nasa left half plane pa rin siya, sorry. Nasa left half plane pa rin siya. Okay. So pero what happens kapag ang kinonsider natin is itong reciprocal ng roots ninyo. Okay. Tingnan natin muna ito. Kung ang roots ng polynomial ninyo ay -3 tsaka -2, yung polynomial that would result to those roots are s plus 2 at saka S plus 3. Okay? So, verify natin na itong S plus 2 at S plus 3 would give rise to the roots negative 3 at saka negative 2. In which, pag minultiply natin to, this becomes S square plus 5S plus 6. Okay? Pero, pag tinignan natin itong polynomial na panggagalingan ng mga roots na to, that should be coming from S minus 1, S plus 1 half at saka S plus 1/3. Okay, in which pag minultiply natin yan, that becomes S square plus 1 half plus 1/3. Okay, pag inad natin yung 1 half at saka 1/3, 1 half plus 1/3, that should be 6 ang LCD. So this is 3 plus 2. 3 plus 2. So that should give us 5 over 6. Okay. So this is 5 over 6S plus this is 1 over 6. Okay. Or pag minultiply natin to sa 6, basically. Okay. Pag minultiply natin to sa 6 para ma-eliminate yung mga fractions. Okay. This becomes 6 S square. Okay. Plus 5S plus 1 over 6. Okay. Ngayon, pansinin natin ito at saka ito. Okay. Anong mapapansin natin sa coefficients nila? Mapapansin nyo na kung ito, kung isusulat natin sa array yung coefficients, so that is 1, 5, 6. Okay. Ito naman, kung isusulat natin sa, ignoring the denominator, okay. Kung isusulat natin sa denominator, sa array yung nito, this is 6, 5, 1. Okay. So, ang papansin natin na yung inyong coefficients, okay, pag in-arrange natin yan in reverse, okay, in reverse, yung roots nun, okay, would actually be the reciprocal of the roots of the original polynomial. Okay? So, ito yung isang technique na pwede natin gamitin ngayon dito. Ang gawin natin is, isulat natin itong denominator nyo, okay, instead, using the reverse coefficients. Okay? So, in that way, makukuha natin yung location ng reciprocal ng roots. And again, kung yung reciprocal ng roots nyo naman is, hindi naman nababago yan kung nasa left half plane siya o nasa right half plane siya. Okay? So dito, kung ito yung binigay sa ating, ito yung binigay sa ating denominator, okay, in which ang ating coefficients ay, ang ating coefficients ay 1, 2, 3, 6, 5, 3. Okay. Sulat natin siya ngayon as yung reverse niyan. Okay, which is 3, 5, 6, 3, 2, 1. Okay? So, yan yung susulat natin ngayon. Or yan yung ilalagay natin ngayon sa route table natin. Okay? So, in which case, we will have the following. So, ayan, 3, 5, 6, 3, 2, 1. Okay. In which, kapag pa-verify na lang, na kapag kinumpleto nyo yung route table, wala kayong may encounter na 0 only in the first column. So, kapag gano'n, mas maganda. Pero, don't, possible pa rin na mag-0 only to on the first column. Posible pa rin yan na kahit balik rin nyo siya, gano'n pa rin yung mangyayari. Okay? So, ayun. Pero in this case, hindi kasi nangyari yan. So, mas maganda. So, dito, mababasa natin na meron pa rin 2 sign changes. So, meron tayong dalawang sign changes dito. Okay, so ito, tsaka ito. Okay, so merong 2 sign changes. Okay, meron 2 sign changes from here to here, tapos from here to here. So, yung number of sign changes natin is still 2. So, ibig sabihin, number of right half plane poles natin is still 2. So, yung number of left half planes pa rin natin is 3. So, papansin nyo, doon sa tatlong methods na ginamit natin, pare-pareho yung nakuha nating conclusions. Okay? So that is meron siyang dalawang right half plane pulse sa tatlong left half plane pulse. Okay? So, yun yung mga methods ngayon na pwede nyong gamitin. Okay? Para ma-evaluate kung sakaling magkakaroon ng entire row, magkakaroon ng zero dun sa first column ninyo. Okay? Una, epsilon. Pangalawa, magpalit kayo ng very small positive at saka very small negative number. Pangatlo, i-reverse nyo yung coefficients ng polynomial niyo. Okay, so those are the three methods na pwede nyong gamitin para ma-solve yung ating route para makompleto niyo yung route table para doon sa ating 0 on the first column.
May question tayo dun sa first case natin. Sa first special case pala. Okay, so kung wala, let's continue on dun sa second case naman.
Okay? So, yun. Now, let us proceed dun sa case na na yung entire row ninyo ang mag-zero ngayon. Okay, so yung kanina, first column lang yung nag-zero. Okay, in this case, we will proceed now with the case na yung entire row ninyo mismo yung mag-zero. Okay, pero ang gawin muna natin is that, let's proceed with an example in which papakita natin kung paano ko kumpletuhin muna yung route table. Tapos later on, kung paano siya i-interpret. Okay, so let's complete the route table for the following closed-loop transfer function. Okay, so in this case, we will have 10 over s raised to 5 plus 7 raised to 4 plus 6s raised to 6s cubed plus 42s squared plus 8s plus 56. Okay, so initially you would have 1, 7, 6. Okay, you would have 1, 7, 6, 42, 8 at saka 56. Okay. So, yung 742 at saka 56, pwedeng i-divide yan ng 7 para maging 1, 6 at saka 8 siya. Okay. So, obviously, pag kinompute nyo ngayon yung tatlong elements na yan, magiging ano yan, 0, 0, at saka 0. Okay. So, kasi pareho yung identical yung first two rows eh. So, kung identical yung first two rows, obviously, yung pangatlong row nyo would be 0. Okay. So, paano natin kukumpletuhin ngayon kapag ka nag-0 siya? 0, 0, at saka 0. Ang gagawin natin is babalikan natin yung nasa naunang row, yung preceding row. Okay. Tapos from there, magsusunod tayo ng polynomial galing doon. Okay. So yung polynomial na galing doon, isisimulan natin dito. Okay. Which has ito yung coefficient ng s to the fourth. Tapos magdi-decrease yan ng dalawa. Okay. So maglalaktaw yan ng power of s. So kung s to the fourth ito, s square ito, tapos ito constant to. Okay? So ganoon din dito pag i-interpret niyo to. This is s to the fifth, s cube, tapos s ito. Okay? So since ito yung concern natin, tong s to the fourth row, this is s to the fourth plus 6s square plus 8s, plus 8. Okay, so ito siya. Now, what we will do from there, pag nakuha na natin yan.
Maliwanag yung part na yon. Yung pagkuha ng polynomial kapag ka nag-entire row 0 siya. Mukhang isa lang ang nakakuha. Dalawa, tatlo. Okay, so mukhang maliwanag naman ha. Sigurado kayo. Okay, so sige. Tuloy natin ha.
Okay, we will differentiate this one. So yung derivative nito with respect to s is 4s cubed plus 12s. Okay. So yung 4s cubed plus 12s, yan yung ipapalit natin. Itong 4 at saka itong 12. Yan yung ipapalit natin doon. And of course dito 0. Okay. Papalit natin yung 0. But itong 4 at saka 12 kasi is divisible by 4. So, palitan din natin, divide ito by 4, so magiging 1 siya. And then, divide natin itong 12 by 4, magiging 3 siya. So, ngayon, ang magiging, ano nyo ngayon, ang magiging row nyo ngayon dito is 1, 3, at saka 0 na. Okay? And then, pwede na kayo mag-proceed ulit. Okay? So you continue that, you continue on that by completing the route table. So ito yung magiging completed route table niyo. So paki-verify na lang. Okay. Yun. Okay. So now, that's how we complete yung that's how we complete the route table of of the case where meron kayong entire row na 0. Okay. So paano natin siya i-interpret ngayon? Ganito. An entire row of zeros will appear in the route table when a purely even or a purely odd polynomial is a factor of the original polynomial. Again, magkakaroon lang kayo ng entire row of 0 kung yung original polynomial nyo is factorable into factors, one of which is a purely even or a purely odd polynomial. When you say purely even polynomial or purely odd polynomial, it means ano siya? Halimbawa, yung s to the fourth plus, ano yun? Yung nakuha natin? 6s square. Okay, 6s square plus 8. So, purely even polynomial siya dahil yung powers ng s niyo are all even numbers. I-include nyo na rin yung s raised to 0. Okay. So, kapag pag ito, yung isa sa mga factors ng polynomial nyo, or ng original polynomial niyo, magkakaroon ng entire row of 0 sa kanyang route table. Okay. So, what would happen next is this. Itong even polynomial nyo ngayon, okay, yung even polynomial nyo ngayon, pag kinuha nyo yung poles niyan, okay, since even nga siya, ang mangyayari dyan is yung mga poles niyan symmetrical. Okay. So, kung symmetrical siya, ibig sabihin, halimbawa, meron siyang pole dito sa left half plane. Automatic na meron niyang counterpart na pole sa right half plane. Okay? O kaya, kung meron niyang complex pole dito at saka dito, okay, automatic na meron niyang asymmetrical dun sa kabilang side. Okay? Or, kung meron siyang pole dito sa j omega axis, magkakaroon siya ng counterpart dun sa ilalim. Kasi nga, symmetrical siya. Okay? So, even polynomial gives rise to to symmetrical poles o symmetrical roots. Okay. And in that case, ito yung kaisa-isang case out of the 3 na diniscuss natin. Basic, 0 on the first column, at saka ito. Out of these 3 cases, ito lang yung case na magkakaroon kayo ng pole sa j omega axis. Ito lang yung possible case na magkakaroon kayo ng pole sa j omega axis. Okay. So that is why we should be in the lookout of the fact na kapag nag-entire row 0 kayo, kailangan open tayo dun sa possibility na meron tayong j omega axis poles. Okay? So ayun, yun yung isang dapat natin tandaan sa case na to. Again, yung entire row of 0 of the route table is due to the fact na yung original polynomial nyo has an even polynomial factor. Okay, in fact, in this case, okay, sa case na to, ito na actually yung pinaka-even polynomial factor niya. Yan na yun mismo. Okay. So yung other niyan, meron pang isang factor yan in which that would correspond dun sa others natin. Or dun sa other factor natin. Okay. So ayun. And then, this even polynomial, okay, would give rise to symmetrical poles o symmetrical roots. Okay? So kapag symmetrical root siya, basta meron siya sa right half plane pole, meron din siya sa left half plane pole. Pag meron siya sa pag wala siya sa right half plane pole at left half plane pole, ibig sabihin nasa j omega axis siya. Okay? So ayun. Ngayon, ang gagawin natin kapag naintindihan niyo 'yon sa case na to. Kapag meron kayong even polynomial, titingnan nyo kung meron siyang right half plane pole.
Pag wala siyang right half plane pole, dahil nga sa symmetry, automatic wala siyang left half plane pole. Okay? So kapag meron siyang right half plane pole, meron siyang left half plane pole dahil sa symmetry. At pag wala siyang right half plane pole, wala rin siyang left half plane pole dahil sa symmetry. Okay? So, ibig sabihin nun, ang gagawin natin is bibilangin natin kung ilan yung posibleng nasa right half plane at saka left half plane. Tapos yung hindi natin mabibilang dahil sa kasi unang-una alam natin kung ilan lahat yung poles meron ang even polynomial ninyo. Halimbawa in this case, ilang poles meron ang even polynomial yun na ito? So meron tong apat kasi s raised to 4 eh. Ito lang, itong even polynomial nyo lang na to. So meron kayong apat na poles galing dito. Kasi apat yan eh. Okay, s raised to 4. Tandaan nyo, ang number of roots ng isang polynomial nakadepende sa highest degree. So ito, ang highest degree natin is 4. Therefore, ang ating number of roots para dito sa polynomial nito ay 4. Okay? So halimbawa ganito. Nakita nyo ngayon na itong ano na to, itong polynomial na to, merong isang right half plane pole. Okay, merong isang right half plane pole. Automatic meron yung isang left half plane dahil sa condition ng symmetry. At ang nabilang nyo lang kasi is right half plane, isa, left half plane, pangalawa. Meron pa kayong dalawang hindi nabibilang. Yung dalawang hindi nyo nabilang na yun yung nasa j omega axis. Okay? So, ganun natin siya tinitingnan. Okay, so tingnan pa natin yung mga further examples para mas maintindihan pa natin siya. Para ma-interpret natin ngayon, finally, yung ating route table. Okay. Ganito ang gagawin natin. Itong route table natin, okay, lakayan natin. Ito yung route table natin, nahatiin natin ito sa dalawang parte. Una, yung parte kung saan meron kayong even polynomial. So again, ang even polynomial nyo has a degree ng s raised to 4. Okay. So simula sa s raised to 4, pababa. Okay. S raised to 4, pababa. Yan yung even polynomial nyo. Okay. So that's 1. Yung other half nun is ito, yung others. So simula dun sa taas hanggang dun sa even polynomial ninyo. Yan. Yan yung others ninyo. Okay? So, pag in-interpret natin siya is, i-interpret natin separately yung others at saka yung even. Pero tandaan nyo dun sa even, there exists this possibility na meron kayong j omega axis poles. Pero sa others, wala kayong possibility na ganun. Okay. So, yung others, we interpret it normally as the basic route table. Pero itong even, titingnan natin yung possibility na meron kayong j omega axis poles. So, paano siya? Ganito mangyari. Sa even polynomial niyo, 'di ba wala kayong sign changes? Tama. So kung wala kayong sign changes sa right half sa even polynomial niyo. So even kaya natin sa even. No sign changes sa even. Kung wala kayong sign changes sa even, ibig sabihin wala rin kayong right half plane pole. Okay, wala kayong right half plane pole. Ibig sabihin wala kayong right half plane pole. Okay. Ngayon, dahil sa requirement ng symmetry, kung wala kayong right half plane pole, obviously, wala rin kayong left half plane pole. Okay, wala rin kayong left half plane pole. Kasi nga, kailangan, under ng even polynomial, kailangan symmetrical siya. Okay. So, kung wala kayong right half plane pole, wala rin kayong left half plane pole. So, kung wala kayong ng dalawang yan, nasan ngayon yung poles nyo? Nandun sa j omega axis. Okay, nasa j omega axis yan. At ilan ngayon yung nasa j omega axis niyo? Since ang even polynomial niyo has a degree of 4 at wala kayo sa right half plane at left half plane, lahat yun makikita nyo sa j omega axis. So, 4 yung makikita nyo yung poles dun. Okay? So, ayan. That is for the even. Ngayon, yung others, we interpret it normally. Sa others, wala kayong right half plane, wala kayong sign changes. Okay. So, ibig sabihin, wala kayong right half plane pole. Okay. And then, lalabas ngayon, yung left half plane, yung ano nyo, left half plane pole ninyo, yung pole nyo, nasa left half plane ngayon. Kung wala siya sa right half plane, nasa left half plane siya. So, isa siya. Bakit isa? Kasi s to the fifth, okay, s to the fifth yung ano natin, yung ating degree. So, lumalabas ngayon, kung s to the fifth yung ating degree, ganito yan. Ito. Hati siya sa dalawa, no? Even. Ito yung mga possible locations natin. Left half plane. Okay. Tapos, we have right half plane. Tapos, meron kayong J omega axis. Okay. Tapos, meron siyang dalawang possible source. Okay. Meron siyang even. Meron siyang others. Tapos, i-total natin. I-total natin siya. Okay. Now, sa even, okay, i-total din natin to dito. Sa even, since 4th degree, yung total of number, since 4th degree yung even polynomial ninyo, 4 yung i-expect nating number of poles dyan. Okay. So, since lahat-lahat, dahil 5th degree yung original polynomial ninyo, 5 yung ine-expect nating poles. So, yung manggagaling sa others, isa na lang. Okay. So, ayun. Again, sa even polynomial, dahil 4th degree, yung even polynomial ninyo, 4 yung inaasahan nating poles galing doon. Okay. Tapos, since 5th degree, yung original polynomial ninyo, 5 yung poles na hinahanap natin. So, ngayon, kung 4 galing sa even, yung others ngayon, isa na lang yung hahanapin natin galing dyan. Okay. Ngayon, tingin tayo sa even. Again, walang sign changes. Therefore, as a requirement ng symmetry, walang right half plane at saka walang left half plane poles. So, ibig sabihin, itong 4 na to, nandun lahat yan sa J omega axis. Okay? So, ayun. Sa others naman, since walang sign change, walang right half plane pole. And wala naman tong requirement ng symmetry kasi ordinary ordinary or basic route table lang yung interpretation natin sa others. Okay? So since wala naman itong requirement ng symmetry, kung wala siyang right half plane pole, yung isang hinahanap nating pole, nandun sa left half plane. Okay? So that, pag tinotal natin, meron kayong isang left half plane pole, wala kayong right half plane pole, at meron kayong 4 na J omega axis. So all in all, meron kayong 5 poles. So that's how we account now yung distribution ng poles ninyo on the S-plane for this polynomial. Maliwanag ba yun? Yung explanation doon. Okay, good. So, kung ganun, I think kasi 10 minutes na lang yung natin, time natin. So, medyo 22 minutes pa to. So, I think I'll just let you watch yung the rest of the video sa sa YouTube. Okay. Later i-upload ko ito kasama yung recording ng session natin for today. And okay. So, some announcements lang. Regarding to sa quiz number 2 ninyo, ayun, ganun pa rin. Nakaka-encounter pa rin ako ng ng violation sa file naming. Okay. Dati, sabi ko, no answer ang i-upload nyo. Ginawa nyo, yung no answer ninyo, nilagyan nyo ng question code. Ngayon naman, ang ginawa ninyo, pinalagyan ko ng question code. Hindi nyo naman nilagyan ng question code yung file name ninyo. So, hindi ko alam kung saan tayo lulugar. Kung ano yung, ano yung mangyayari, ano yung gusto nyong gawin natin. Okay? So, nasasayang yung oras ko paggawa nung nung automated na pang-segregate ko sana nung files ninyo para automatic na magkakahiwalay na kung ano yung mga question number para tuloy-tuloy sana ako mag-check. Ang mangyayari ngayon, mag-segregate pa rin ako ng mano-mano kasi may mga naiiwan pa sa ibang may naiiwan pa dun sa original storage nyo
Dahil nga, hindi siya masegregate dahil hindi sumunod sa file name convention. So, dagdag trabaho na naman yan sa akin. Okay, so that's one. So, bahala na sa susunod kung ano mangyayari. Okay. Number 2. So, na-upload ko na nga itong na-upload ko na itong ninyo, lecture ninyo. At the same time, may assignment na rin kayo. Okay. I think na i-deadline ko yung homework ninyo ng na-deadline na ko siya ng October 27. So ang magiging quiz natin is basically October 28. Okay? Pero ang mangyayari nito is yung October sa time na yan, makakapag-discuss pa tayo ng 3 topics basically. Pero ang isasama ko lang sa quiz number 3 ninyo, 2 topics lang. So dalawang homeworks lang yung magiging due ng October 27. Okay, ito, stability, tsaka yung steady state error. So, yun yung magiging 2 homeworks na magiging due nito. So, yun din yung magiging sakop ng quiz number 3 ninyo. Okay, pero magsisimula na tayo mag-discuss ng next topics after ng steady state error. Okay, so para mas mas efficient tayo sa paggamit ng oras. Okay. And then number 3, announcement number 3, regarding sa sa midterm exams niyo. I am thinking na baka either pagsunurin ko na lang yung midterm at saka final exams niyo o kaya pagsabayin ko siya. Kumbaga parang nasa isang exam na siya pero meron dong mga parts na naka-identify para sa midterm. Meron dong mga parts na naka-identify para sa finals. Okay, so hahatiin na lang natin yung yung exam niyo para sa midterm at saka sa finals. Okay, so ayun, yun yung isang natin. Isang option natin. So, baka later on talaga tayo mag-midterm exams. And number 4, may papagawa ko sa inyo regarding sa isang homework niyo. Baka itong homework ng stability. Okay. So, anong gagawin? I'd assign you or I'd let you group yourselves into 3. Into 3 or 4 persons siguro. Okay. And then I would like you to meet. Okay, mag-meeting kayo through Teams na ang gagawin niyo is to discuss your answers dun sa mga answers sa mga questions sa homework niyo tungkol sa stability. Pero i-announce ko pa yan on a later date para mas malinaw yung mechanics. Okay, kailangan ko lang yun kasi dahil ipang-i-exhibit natin sana sa accreditation. Okay. So, doon lang naman ako magre-require ng ganun sa homework number 8, sa week 8 homework niyo. Okay. So, pagkatapos hindi ko na ulit i-require yan. So, ayun. I-announce ko on a later date yung mechanics, pati kung kailan siya kailangan. Kung kailangan yung recording ng video ninyo para doon. Okay. So, kayo na bahalang bumuo ng mga grupo ninyo. Para pero kailangan talaga masagutan niyo na tong homework na week 8 homework niyo. Okay, so as much as possible, please do answer this as early as you can para magamit or maisalang na natin siya sa group discussion niyo. Okay? So, yun lang yung mga announcements natin. Yes, Mr. Habil, may question ba? Okay. So kung wala ng questions at yung iba ba? Meron bang clarifications or meron bang gustong i-clarify? Okay. So kung wala na, I think we can dismiss na for today. Ayun, just continue on studying and ayun. Continue on studying and thank you for attending today's meeting and ingat kayo lagi. Okay? Thank you. Please leave the meeting na lang after you Okay, sige. Thank you din.